this time he is going to talk to us about a very current subject, which is what is the best voting system. So please.
So thank you everybody for coming. Sorry for the small delay. Okay, so things that essentially we will not cover in this talk will be things like, what was the name, division methods or gerrymandering. So we will focus in a more simple kind of questions, which is given a group of people, you have certain alternatives, how this group of people should agree on a collective choice. So making this more concrete, the question that we will focus is, given a group of people and a set of alternatives, so the group choose a collective choice. I mean, classical examples, you are a group of friends, there are like 5 possible bars or places that you have to go, and then you have to agree on a common bar to go. Other thing that can be, you organize a party, people have proposed several songs, and then, for example, you have to agree on which is the first song that you play, which is the second song that you play, which is the third song that you play, and so on. Or if you want more politically things, you are in a political party, you are going to present yourself to elections, you have to decide which is the order of the people in the list that will go in the ballot that people will vote. Okay? So let's start with a little bit of formalism, because in order to talk about this. So about the formalism, usually what we will use is some sort of, we will do certain set of assumption on the voters and on the alternatives that we have. So we will have some, that I will call set of alternatives. This will be S, and we will assume that in general we have M alternatives. Okay. This is a letter like any other one. Then we will have a set of voters. This is nothing special. This set of voters, we will denote them by numbers. So we will have voter 1, voter 2, voter 3, etc. Now the more strong assumption is the following one, which is regarding the preferences of the voters. So in general, when you have to decide, you are not always so clear if you prefer some option or another. Sometimes you are indifferent with regarding 2 options. You can say, okay, I don't care if I go to this place or if I go to this place, I don't care if this happens or this other thing happens, or maybe you don't have even an idea of how one option compares to the rest. I mean, all these things can be taken into account, but for simplicity here, for exposition purposes, we will just assume that the preference of its voter its voter I is a total order on S. So what I mean with this, whenever I will write something like this will just mean by definition that voter I prefers Y to X, and then the total order thing just means that we are making some set of assumptions. I mean, this will be in a strict order, so I will assume always that something like this. This is just formal, so voter I does not prefer x to x. Then some that either, so let's put here x different than y, then or so essentially this means that a voter either prefers y to x, or either he prefers or she prefers x to y. And the last one is that if a voter prefers y to x and they also prefer y set to y, then they must prefer set to x. I mean, this kind of things is not always the case, but this is what we assume. Like, in a way, you have a clear first favorite, then you have a second option, then you have a third option, then you have a fourth option. So this is more or less what we will be assuming here. So put in a little bit more of analysis in here. So, okay, so we have all this set of choices, we have here an order, etc. So now we come to the more important thing. So let this PI be the set of possible preferences. And let this P equal to this product be used the set of lists of preferences of the voters. So these elements usually we have something like this. And here what we will be interested in is in what is called a social choice procedure, that whenever we are given some set of preferences, we will just select a subset of S, usually non-empty. However, when we put this, we assume that maybe there are some procedures for which you don't have a clear set of choices to assume. Okay, so we select 1, 2, 3, n, and then we select something. Now we will see examples. And the social choice procedure is essentially what we use to decide in a certain way. Now I will put examples of this to illustrate what I mean by this formalities. And usually any element, any x belonging here, so whenever I have an element in this set, I will just say is a social choice according to this is not so important right now. Okay, so usually here we are just also, this is another restriction that I do for simplicity. So instead of ordering all the elements of S, so saying, okay, what is our first option, second option, etc., I just focus on what is the first option of the group, and I'm allowing that there can be draws. This is why this is a set and not an element. Maybe there is people who is undecided if they prefer one element or another. So then these two things goes together in the set, and that's all. Okay, so this is the social procedure, and now let's start with a more concrete thing. But first, let's rewrite the question. Just now, with the formalities and all these things, give it a group of voters, etc., is essentially what is the best social choice. Of course, still we need best because we still don't know what does that mean. So now let's start with what I will call illustrative example. This is here. So in this illustrative example, we will have a set, our set of alternatives will be simple. Let's just put some colors on it. So will be yours A and B, then C and D, and then E. Okay, and we will have a simple set of voters which will be used in this example will be 7. So we will have 7 voters. Of course, this thing here, this is usually how you don't write in examples. You don't write a formal relationship. What you just write is the order of the choices. So then the way in which we will have the preference of the people will be as follows. A, and then here will be at the end. Here, here, and then here. Then we go with B. So B will be there, and B will be there, B will be there, B will be there, there, then we up there, then B here, C. Here, see there, see there, see there, see here, and see here. And of this we come with D. Last one, but not less important, is E. Okay? So essentially, we have here 7 voters. So voter 1 will prefer A to B, then B to C, then C to D, and D to E. Voter 2 will prefer A will be the first option, but the difference with the other voter, D will be its second option. So we can see that, for example, here voter 2 and voter 3, they have essentially the same preferences, so they will agree. And yeah, then we have different sections. So this will be more or less the example that we will be coming back to see how the different methods differ on what to do that. So now we will start defining the different methods that we can have. Okay. So let's erase this. And let's start putting the examples. So the first example, so let's put here 1.1. Condorcet's method. So saying this in a way that is more or less understandable in natural languages. Yeah. So we say S belonging S is a social choice. Social choice if for all other T belonging S, so for any other alternative, no more than half of the voters prefer T to S. So this is Condorcet's method. We do all pairwise compare, yeah?
Condorcet, I believe.
Yeah. Condorcet's method. So yeah, we do all the possible comparison pairwise, and we are okay. S essentially is in every pairwise decision, S has to win to T. So if we go here, we realize, okay, if we compare, for example, first A to B, we realize that B has 4 votes when we compare against A, and A has only 3 votes. So then A cannot be Condorcet's voter. Okay? Now we continue with B, and we compare, for example, B to C. Okay, we see that B still is winning C because it has 4 votes against C. Okay, so then we have C cannot be a Condorcet voter because B has 4 votes against C, and C only has 3 votes against B. So now we do B against D. And then we see, okay, D has here wins, here loses, here wins, here B wins, and here D wins. So then we have here D wins, this is 4. So then B cannot be a Condorcet's winner. And if you continue doing this, you will realize about one of the problems with Condorcet's methods. That essentially when we do this Condorcet, we have no source objects. So no matter how you compare pairways, you will have always another option that has more voters than the option that you choose. So this means this method does not give you anything. Then we go to the next one. This is plurality method. So S belonging is a social choice. If no other T belonging S has more voters that has it as a third option. Than S. So in other words, we forget all the information here. We only focus on the first row. We look which is the options with more votes, and this is the option that we choose. So here essentially A has 3 votes, C1, C2, B1 and E1, so A has the majority, essentially wins. This is just the usual thing, you vote your favorite option and you disregard the rest. So then in plurality, the winner is A. Okay, so now here we have C2. Now we go with another one. It's called Borda counts. And here we can put also an scoring method. So here the idea is whenever we look at this set of choices, we give we give points. And then -1 points for each voter. It has S as a first option. Put here first option. Then we have, so here should be an F. And -2 points. Here is the same, but now here is just second option, and we give n-3, etc. So essentially, the first option will get a certain number of points, the next option 1 point less, etc. And this is for each vote. In this case, we have 5 options. So here A gets 4 points, another 4 points, another 4 points. This is 12 by now. Here A doesn't get any points because it's the last option. Then here A gets 1 more point, so this is 13, 14, 0. So here A has 14 points. Then one can repeat this. I mean, I will not do. So if you count the points, you will see that A has 14 points, B has 17 points, C and D has both 16 points, and E has 7 points. So essentially the option with more points, with 17 points, is B. So in the Borda count, essentially we choose B. Okay, so here another way of examining this is to do, again, pairwise comparisons, as in the Condorcet's method, and this plurality method, but now we care about the number of votes that you get in each comparison. And if you do, one can show that the number of points that the Borda method gives essentially is the number of votes that you get in all pairwise comparisons when you add them up. So you compare A to B. So here, before we say this has 14 points, but here we have, okay, A against B gets like 3 points. No, 4 points, so 4 votes. Then you compare A against C, it gets another 3 points. And here doesn't get any points. Then you compare, and then you are counting all these votes, and you are adding this up, and this will be essentially the Borda count. Then another variation of the Borda count that one can do is, okay, yeah, here you give a -1, a -2, a -3. I mean, you can give whatever other quantities you can give. You can give here m minus m, then m divided by 2, m divided by 4, or whatever. Any kind of the standing procedure, more or less, will be satisfactory. For example, if you look at the plurality method, this will be the same as giving 1 point to the first option and then 0 to the rest. So this is essentially, so scoring methods more or less generalize plurality methods on the other. Okay, so let's go to the next. And this is called sequential pairwise voting with fixed agenda. So here is, as far as I know, is assume S is ordered. For example, in this case, by how we have written S is in a certain way ordered the candidates. So and what we do is first against second. Here we will get some winners, then winners versus third, and so on. So in this case, first we compare A to B, and then we have that A to B, A loses. So okay, we have now B. Now we do B against C, because C is the next candidate. B essentially loses. If this I didn't do, yeah, B loses. Then, okay, so now C is the new winner. Now we do the comparisons. C against D. Essentially, C against D, C wins.
Wait, B beats C.
Yeah.
B beats C.
Yeah, but B has lost against what? B beats C?
D.
Yeah, you're right.
Yeah.
So yeah, B against C, then we got B, then it's B against D. In this case, D wins. And then D against E, D beats. So then in this one, in this, let's call it sequential, we get that D wins. So essentially what you do is first against second, then the winner against the next, and you do like this. It's like an eliminating process by round. And then, let's write it, let's put this up. Let's write this. now, I think, the one before the last, this is what is called 1.5 Harry system. So this essentially is you do the voting and then you eliminate, so in each round, so you go by round, each round eliminate those alternatives that are the first one among the least number of voters. Among the remaining numbers. Those that are the first one among the list. Remaining. So here what we do is, okay, first we look and we are okay, which is the option that appears less time as a first option for the, and then this is the option D. Because D doesn't have any voter here that prefers it as a first option. So then we eliminate D. So here we will just write everything without D. Then we will continue, so the first row still didn't change. Then we will have that the candidates with less voters that prefers them as a first option are B and E, because they only have 1 and 1, so we eliminate them. And then now if I write, I will have a sequence like this, in the since D, C, and B has been eliminated, then we put everything up. So like we eliminate, so then new things becomes first. So then I will get something like this. A, C, 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 C. And then of course the candidate that will be eliminated is A, because now it has less voters as a first option. So then in this harem, we get option C. And the last option, which is probably the easiest to understand, which is dictators. So essentially is one voter choices. So there is a preeminent voter whose favorite option is chosen. So if in this case we will have the dictatorship with the last, it will be the A, here it will be the B, etc. This depends on which is the dictator. Okay, so these are more or less the options, but I mean, eliminating the remaining one, one can see here that we have 5 procedures. 5 procedures that one can more or less think they have some democratic entity, the sense that they care about the voters. But in one of them there is no choice. In the second one, plurality, we get A. In the Borda method we get B. In the sequential method we get D. And in the harem method we get C. So essentially in each one of these different voting systems we get a different candidate. Okay, so then one can ask themselves, what is the best voting system among these? And now this is what I will discuss. So this is more or less the example I want to have in mind. So I will let this up here, so that is clear. Of course, one can be the best method to choose is the method that when I'm decided to which bar to go, chooses the bar that I want to go to. But I mean, this is something that can happen, and one should always be aware that whenever a person proposes a method, it can be a different method than the 16th one. It can be some way of getting the result that you want without actually discussing or just by changing the procedure in which you choose. So now let's start discussion. Which method is better? Now, important thing is, let's go with first two alternatives. So if you check what happens when two alternatives, the Condorcet method, the plurality method, the Borda count, the sequential election, sequential pairwise voting with fixed agenda, and the Hare method, they become all equivalent when you have only two alternatives. Because you just compare them, you choose the one with most votes. I mean, it's nothing in there. And the reason for this usually has some this reason, and this is what is called May's theorem. This is 1952. So this theorem essentially says, okay, so assume that two alternatives of number of voters. This is used to avoid draws. And every election gives a winner. Gives a winner. And then the thing is, so you have this, and this is so you have some social procedure H where every election gives a winner. Such that, and these are the properties that now come. So the first property that I will put will be this called anonymity. It's, in other words, this property says if two voters exchange their preferences, the social choice does not change. This is more or less what is saying all voters are equivalent. So whenever you and me, we vote, we change the things that we vote, it will not affect the decision. So it does not matter who votes what, but which is the amount of people that votes particular things. Then we go to the second one, which is neutrality. And this is the equivalent, but for alternatives. If every voter exchanges two alternatives X and Y becomes a social choice only if X was a social choice. This is in a way saying that the voting system does not have a preferred option. I mean, you could have a voting system which does not matter what people vote, the first option will be always the chosen one. Then, okay, there is a preferred option. So this essentially what it's saying is, okay, more or less the options are treated in an equal way. So this is what this neutrality means. And then the last option is called this. This is called monotone. So this is essentially, so if a voter voter I changes an alternative X that is not a social choice. Lowering their preferences X cannot become a social choice. I mean, the idea of this monotone monoticity is essentially that if some option is not chosen, and then suddenly for one voter this option happens to be worse than it was, then the voting system cannot choose this option suddenly. So we assume that the remaining of the voters, they don't change their opinion about their preferences, but then there is a voter for which a non-winning option essentially becomes worse. This is you saying, okay, this cannot suddenly become the chosen option. Because for all the rest of the voters it was the same, and for one voter it is even now a worse option than before. So this essentially is the thing. So whenever we have these free properties, and we have these things, then H is the majority rule. So what one can see here, with this theorem is saying, okay, when you have two alternatives, there is a proper way of choosing. You vote, and the option with most votes has to be the chosen one. Essentially, these Condorcets, plurality, Borda, sequential voting with fixed agenda, all these methods, the only thing that they are trying to do is taking this advantage of pairwise comparisons, like you compare one against one, then I have a nice method to choose, and they are trying to exploit this to go up. So this is more or less the thing. Do you want to add something?
What was the majority rule?
And this is just that if more than half of the people
Like
chose
plurality.
this. Yeah.
Okay.
This has to be distinguished because when there are more than 3 options, majority rule means you really need the option to have more than half of the votes.
I see.
While plurality, you only need the majority of the votes. There is this slight difference between these two. Okay, so this is the nice result in the case of 2. So now let's put this up here. So here there are things that we want about the methods. There are things that... So the thing essentially is to find properties that one likes about voting methods, and then say, okay, which property satisfies this? So by now we have seen several properties, which is, okay, anonymity, this is something preferred if you don't want any voter to have extra power with respect to other powers. Neutrality is if you want options to be equivalent when you vote. And monotone means, okay, a voter changing an option to a worse position in their list will not get this option elected. Then we have the things that, some extra properties. Here I will just write a pair. This is called Pareto. This is the most, I think, yeah. So you are given 2 options. In S, if every voter prefers X to Y, then Y cannot be a social choice. So if there are 2 options and there is one option that is preferred by everybody to another option, then the second option can never be the chosen one. And this is something reasonable to expect in a certain way. And then there is another one, that's right here. This is called stability. So this option, in a certain way, what is saying, imagine that you have both. You have an option. So is there a way that one voter emitting a dishonest vote, so not giving their actual preferences but another set of preferences, can they get a social choice that is better in their original list? It's like, will you, by lying, by voting, get advantage from the voting system? So writing this in a more formal sense, so we assume that X is a social choice. A social choice for, we have a set of preferences. There is no sigma prima I. So this is the voter I, lies in their vote. They say another preferences, so there is no this. And X belonging so this is okay, we only change, now the voter has both a different guide option, and this is the new one of the new social choices. So now voter has lied, and there is now this, and it such that X, essentially the voter, by giving a different set of preferences, they have obtained a social choice that is better than what they will got if they will vote in an honest way. So you want your voting system in a certain way to motivate honest voting, that you cannot, by lying, get advantage. Okay, so now let's look more or less here in this this. So here we have several ones. So let's try. This was Condorcet. Then plurality, Borda, sequential, higher, and the dictatorship. Okay, so anonymity, neutrality, Pareto, is not here. Relativity. Let's put here whatever we call always a choice. At least there is always a social choice. So this is here. So when you want a system to be essentially anonymity, so all the voters are equivalent, in this option they are, here they are, here they are, here they are, here they are. The only one that they are not equivalent is in the dictators. Like one person being the dictator, another one being the dictator is not the same. Neutrality is satisfying all of this, unless they don't make a difference of what are the levels of the order, then sorry. Neutrality only. This one. Sequential voting is the only one that, because by construction, sequential voting has an ordering. So then if you reorder the terms, you can get away that some candidate that gets eliminated at some point maybe does not get eliminated by eliminating the person that will beat that candidate. Then we go to monoticity, monotone, and then this is set the hair system. Then we go to Pareto. and to non-manipulable systems. Yeah, this I think is one of the saddest things, as I remember. I only have this one.
Condorcet.
No, this was the only one without a winner. So yeah, as far as I remember, yeah, usually all the systems that you have in a certain way that are responsive to what people get, they have some sort of manipulation in them, implicit in them. That's the dictatorship, because the only person who can lie and affect the result is the dictator, which will not result on you lying, getting a better result. Okay, so let's see a pair of examples of how this fails. So one of the, let's write up there. Some classical settings. So one of these will be what is called the voting paradox. So this is, we have three candidates. Let's write So this in a way is like a nightmare situation, because you can see that more or less this is like you permute cyclically the preferences, so there is not a clear way of deciding who wins. And this kind of situations is more or less what forces certain of the bad things that happen in some of them, but really particularly in the Condorcet voting thing, because this essentially is where this voting system more or less cracks down. Like you don't get any choice. Then a system to see more or less a manipulability of something, and then you have this AA, then you got this. Here we put B, and here we have. So let's see, imagine that we are applying here the Borda count. So then when we look at the three people, so A here gets 2 points, 2 times 2, this is 4 points. B gets 5 points, and C gets 6 points. So a way in which here a voter can manipulate the result is, okay, if you are this voter, for you option B is better than option C. So what you can do is, instead of voting A as your first option, you vote B as your first option, and A as the second option. And then you get a draw between B and C, and then you get B into the social choice. So this is an example of how you can manipulate these kind of things. Also, you can expand this example appropriately. It's something like CC. Here we put A, then maybe here GV. Here you can get also another example how with the plurality rule, how you can manipulate it. Because here with plurality rule, C will be chosen, but then one of these voters, used by changing one of their options, they can include an option that they prefer to C. For example, if this now votes for B instead of voting for A, then B will make a draw with C. Okay, so this is things one can continue. on these things, but now let's go to the, let's go to one of those theorems that made the social choice famous. This is it's called Givard. And this was more or less what this says is that if you social procedure always give a choice. Always give a choice. You always give a choice between 3 or more alternatives. Alternatives in such a way that every alternative can be chosen. This is in a certain way a weaker assumption than neutrality. So under neutrality, one option can be chosen, then all the options can be chosen. This doesn't even assume neutrality. It says, okay, for some list of preferences, one of the options will be, for any option, there is a list of preferences that an option is chosen. So this is weaker than preference. Second one is non-manipulable. Then this essentially aids these dictators. Then this theorem has other forms. Well, one of them is Arrow's theorem. It deals when Arrow's theorem is another theorems in this sense. Then you also have Givard's theorem. Givard's theorem is stronger than this, does not assume anything about preferences, so you don't assume that the preferences are well ordered. It holds for arbitrary voting systems with arbitrary assumption on the voters. And then there is a really fun one, which is Givard's 1978 theorem, which deals even more with probabilistic voting systems. In a certain way, what this says is more or less, if you think you can escape by probability using this, it says there is only one way of escaping using probability. You choose two options at random with a certain probability, and you vote between these two options. Or a dictator is chosen at random, and this dictator chooses. So this is more or less what this theorem says. So to end in some maybe positive notes. Let's write to positive results. You want some positive results. One of them, you can look at Maskin's theorem. I will not enter in what this theorem says concretely, but it says that in a certain sense, so where in a certain sense means if you want that your voting system is receptive to how the preferences of the voters plus neutrality and being anonymous, plurality is the best voting system. Here it's important that we are adding this extra property. And this extra property is certain thing, and this is you saying, okay, if you extend your domain of things to which certain properties will hold, more or less it has to be the plurality system. This I will not enter. Another one is Young's theorem. It's again, we have this anonymous and neutral, and then it shows it has this what is called how is it called? Consistency. This means that this is a scoring method. So you give points depending on which position you are in the rank of each voter, where this consistency just means, imagine that your set of voters is divided in disjoint. So you take your voters, you put a group of them in one room, another group in another room. They decide which are the favorite alternatives, and then we have something like this. That they are decided in a non-empty way, so they are common choices. And this implies that the choice of the full group has to be the intersection of the choices. I mean, this can be reasonable under certain things. And then here the Borda count among these has the special property that if in any pairwise comparison you have a draw of votes, then you choose everything. So this is when you are completely undecided. Whenever there is a draw, for every pairwise comparison, you choose everything. This is what characterizes among these scoring methods. The Borda count. So more or less, summing this up, depending on what properties you are interested, you get one voting system or another. Then more or less all the impossibility theorems what are saying is, okay, you have to do certain choice in which properties you value more and which properties you value less. So more or less one can say, yeah, there is not exactly a best voting system. Because whenever you are choosing a voting system, you have to specify, okay, what you want for it. And some properties that one will probably agree that everybody wants, like this non-manipulability, this everybody can be chosen, and you always choose something. Essentially gives you the dictatorship, so it means, okay, one have to reject some of these. Usually what one accepts is like, okay, voters can vote in a dishonest way and gain something about it by what is called tactical voting. But more or less, so this is more or less, be aware that there are several ways in which you can choose a voting system. More or less, some of them will satisfy some properties, some of them will satisfy other properties. And one should always be careful whenever a person is choosing a new voting system, because by the choice of a voting system, you more or less can modify the outcome of the election without affecting in any way the preferences of the voters. And that's all.
So, are there any questions? I have a question. So various of these methods are actually put into practice, I guess, right? And are they chosen like by historical reasons, or are they really are they put into practice because of certain? Because they satisfy certain properties, and that's what the people want.
Some of them are because people want certain properties, and some other properties they don't want them. So I think the more historical ones are these Condorcet's voting and the Borda count method and the plurality one. This one I think is used somewhere in Australia, if I remember correctly. Sequential voting, there is not strictly it, but for example, if you look, French presidential election is kind of a sequential voting. So first you do a plurality voting, you get the two most voted options, and then you do a final showdown between these two options. So yeah, many of them is, the moment they decide, we do this kind of voting procedure. But also one have to take into account that many times when you vote in a parliament or whatever, you are voting yes or no. And then more or less you have May's theorem saying to you, that's not matter. There is only one method for voting in favor or against something. So more or less that's the reason.
I think there's a question here.
I have a question from a political viewpoint. Is there any definition where the gap between the preferences is? Because if you compare the pluralist model to the Borda model, I mean, it makes a huge difference if you have a huge first preference and the second and third one, you really hate them, so there's not a huge difference between them. Or if you have small differences, and this makes also difference which mechanism you choose.
But this is covered by, for example, when you look at this, so this you can do more what is called Utilitarian View, in which, or even assuming non-discrete or even assuming bigger differences, but the problem is the impossibility results, even when you are more creative on how you put the orders in the preferences, more or less you don't escape. Because here this Givers Sutter-Weiter theorem more or less applies to this thing where you assume there is some strict ordering in each voter. So if you have a first option, second option, third option. But then when you go to this Givers theorem or Givers 1978 theorem, they don't care about how the set of preferences is represented in the mind of the voter. They only care about what are the strategies that the voter can do and what are their desired outcomes in a very general way. So but I mean, there is a lot of variations on these scoring methods and so on. For example, you can have one in which you give n points and then you give very few points to the rest of the options. Or also you can have one if you put several options at the same place. Example, one option that I didn't talk here is what is called approval voting. So in this option is you vote the candidates that you want. You can vote several candidates. So you don't vote only one. And then you choose this, and then the rest you don't vote them. This, for example, here you have a set of candidates that you want, a set of candidates that you don't want. And this is more similar to what you are saying.
Okay, how about, I think that each voting system, I can assume it's a voter, and then apply a voting system for those voters. So, in a sense, combining all the results, But then I assume I need a voting system that also takes in account non-total orderings.
Yeah.
Right? Okay, but do you know results like this?
I mean, these two ones.
These two.
Givers theorem, one should not be confused with this version really complete. Like, this version is more general, doesn't assume any order in the preferences, like even does not assume partial order or good properties in the order. And this one even does not assume that the system is deterministic.
Okay.
Like even includes probability in it. Like this is, probably this is the weirdest name for a theorem. Like, because
The books with common formulation of the names, and so they're well remembered, so it's okay. It's okay, the name it's okay.
No, but I mean the second name of the theorem is usually weird in the sense that it's not common for a mathematician or whatever to have a theorem named after the year, put in the year in which you proved the theorem. It was quite of because they had to distinguish between this one. That was also quite powerful.
Does it exist? Okay. if we give the criterion, you know, that it's anonymous, neutral, and so on, and then could we build a voting system so that many of these are? Now, I mean, here we see a voting system that agrees that has 4 properties.
Yeah, I mean, in general.
I mean, could we be, because the voting system that you presented, they're more or less logical. I mean, but could there be a, I don't know, a not that obvious system but that has more properties, like 5 of them or more?
I mean, the problem is, the thing is, this theorem more or less what is saying, this line you cannot fill it. Of course you can put extra properties like here, you put consistency, then you get a scoring method. Like, there are ways, but you have to consider new properties and to make a new argument. But then the thing is not only, okay, I choose a property and this property, then you also have to argue why this property is desirable among the set of properties that a voting system can have. Because it's not only that, this lives in some abstract thing, the more properties the better. Maybe you prefer a system that satisfies some good properties that you consider represent better democratic values or the values that you are interested in the moment, than but then use having a lot of properties, which is not so clear which is the advantage of having them in a group to decide.
Yeah, and I think one thing that's a little bit less mathematical that is brought up sometimes when these topics come up is transparency, right? So you also, something which is desirable in a society is that it's easy to check. So if you build a very complicated system, then you lose that transparency.
Richard Feynman, the famous physicist, once said, well, universe is a complicated thing. I think Einstein agreed on that one as well. He said, I cannot explain the universe in 2 days. No, in 2 hours. But give me 2 days and we have good results. You know, I mean, he made lectures, and for 2-3 days, if you're consistent with him, and then you understand a lot. But for 2 hours, it's, I mean, but a good point. A good point.
Any other questions?
I had a couple. I was questioning the non-manipulability property. For me, it seemed to be random because all of the other properties are sort of static. So you make like one roll of one pole, and then you fix it and you work with the results. Whereas non-manipulability suggests, like, what if later on, after you threw the dice once, one of them can like permute his choices. So first, it's kind of like not static of all of the properties.
Yeah.
And second, it's a bit arbitrary. Why is it like only one of them can permute? Why do we not say that it's like, I don't know, n of them or etc.?
Yeah, I mean, all these things, there is arguments about them in the sense like, because of course you have many systems are manipulable, but then the question comes, how manipulable are they? Yeah. And not all the systems are equally manipulable. And usually manipulability is not always something like it has a lot of importance when there is a lot of previous discussion in a group. Because if you are in a group and everybody is defending their positions, etc., then in a certain way you get a lot of information about the preferences of the other voters. So then you can take advantage of these manipulability properties of a system. But if you have a system where you use meet and vote, it's not so clear that you can exploit that the system was manipulable in the first place. Like, this is why I mean, you have to reject some properties, and usually the property that people reject is this non-manipulability. Because when you look at this kind of theorems, usually they tell you, okay, every alternative can be chosen, which is weaker than neutrality, but if you want neutrality, you want this. Then you also want some anonymous, but also you want that there is always at least some choice. Mm-hmm. And then this theorem says to you, okay, if you don't want a dictatorship, you have to accept some manipulability in your voting system. So usually the manipulability thing is something like, it would be amazing if you have it, And then the theorem told you, yeah, you don't have it. But yeah, it's true that there is a lot of, some of these properties, one of the ones that is a little bit more fishy in that sense. Like people is, yeah, maybe has some degree of manipulability, but that's maybe not the most important thing of the voting system, that one voter or how probable is this. Because also here all the analyses are deterministic. Like you don't even, here for example, we are not even considering like how often can this be done. Which also it can be very, very unlikely when you have a lot of voters and that you are just in a position that you just change one and then, yeah, that is kind of, so.
I just, second thing I wanted to ask is there a way to sort of mathematize the choice of the choice of the set of sort of requests that you have against your voting system? So in a sense, is there a way to address which theorem would be better for choosing the best voting system, so to say?
I think this depends a lot on the situation. Because for example, if you are with friends and you have to decide the bars, for example, this theorem, one consequence is, yeah, you can be, okay, at random we choose a person and this person chooses which bar to go. And maybe that's the case for choosing the bar that you go with friends, you don't care so much about not everybody having a voice if you avoid having a discussion of 1 hour every night to where to go. But maybe this solution is not good enough when you want to, I don't know, decide which kind of policy you apply to the environment. This depends a lot, many times has all these subtleties of which is the context in which you have to decide.
Do you have an example showing that Condorcet is mappable?
And this is what I was thinking. This probably is, yeah, I think that
it's non-mappable.
Yeah, I think that probably this is non-manipulable. Usually the problem of the Condorcet methods is that
there is no result from time to time. But if there is a result, I guess everyone would agree that it must be the best.
This is another property usually that is chosen. Like there is systems in which one can put here another property with this. If there is a Condorcet's winner, then this system chooses that winner. At least that is a social choice. This is another thing that one can add as a desirable property. Sometimes one can say, yeah, you should choose this one. Sometimes it's not so clear. For example, Borda system is not a Condorcet. Borda system can have a winner that is not a Condorcet winner. And another systems can happen the same. So you can have systems that even though they have some nice properties, the Condorcet, because the Condorcet winner a certain way does not care about how much you prefer an option to another option. While Borda method really cares about how much you prefer one option to another option in your list.
I get a question which goes somehow in this direction. It's, well, when a method fails to have a certain property, then this is because of a certain set of, how do you say, of preferences that make this method fail then. Right? Okay, so maybe some of the methods, their failure sets have a good structure. So you can somehow predefine that if we are not in this scenario.
Yeah,
well, I mean, we without explicitly giving, I mean, if there is a good structure.
For plurality voting, you have something like that, which is one of them is called sense theorem, and one, if my memory does not fail, is called Black's theorem. It says if the set of options or the preferences satisfies certain properties, you are in a good situation.
Yeah.
But this, for example, this masking theorem is even stronger than these two, like it says it has. But it's not an easy theorem to state, so I will not enter on it.
Yeah, sure. Okay, thanks.
So, any more questions or comments?
If not, let's thank Josué again.